Good morning, everybody. People will start coming, but usually at the end, the second day is going to be a little bit late. They will come, but but with the time, because of the due to the time, we will start. But we are uploading. His PowerPoint is very big. Some simulation or something. Oh yeah. But yeah, for Professor Wu is always big. Yeah. Yeah. Right. So this morning we'll start with continue from yesterday with the expert from Taiwan. First speaker, he has a new title, so I have to look at Professor Lin Changyao. Now he's CEO of Air Quality Research Center. So with the new title now, and he's the expert in the atmospheric chemistry, air quality. Yes. So the floor is yours. Then. Yeah.
Morning. Sorry. Today I'm going to talk about the biomass burning issue, especially from China. Why we consider this issue? Because of the biomass burning, actually contributed about 15 to 30% of the entire troposphere CO background, and also biomass burning also has high AOD over East Asia, and also you can see is approximately 20 watt meter squares at one base. We can reduce to the aerosol, so it has a very important role for the biomass burning. Okay, this is just a statistic for the Indochina, this region. Yeah, this region. So the annual fire hotspot number by hotspot actually more than 10,000, or say by a fire hotspot every year for East Asia region. This is just an example for the 2018. So this is a quite active fire hotspot during this year. So we have later I will introduce more details. Have the air pressure measurement this region, and also in Taiwan we have high mountain. This is the mountain here, nearly 3,000 meters high. We can measurement by high concentration seasonal variation for the CO, ozone, and the PM10, especially for the March. You can see is the high mountain has a high concentration, which means it's a background transport. So this is very important roles. But where it come from? This kind of biomass burning product, and also you can see the composition for the OCCO also quite high during the springtime. Okay, so in my previous study, we introduced sometimes you can see the high ozone concentration here, nearly 4,000 meters high. The ozone sounding, you can see is the high ozone nearly 120 ppb, and the humidity is quite high, which means if you check the wind flows, actually from southwesterly, which means in high elevation, they transport from western position, like the certain location like the Indochina area. But when we talk about the transport, you can clearly see the cross-section here, if you from A to B, so you can clearly see the at the lee side of the mountain, the wind speed, the contour line's wind speed can induce strong upward motion, then bring the biomass burning product to the high position, high elevation, nearly 700 Pascal, which means around 3,000 meters high. So here we would like to ask two scientific questions. One is how's the effect of this kind of rolling transfer biomass burning from China to Taiwan and even East Asia? And this, question two, can biomass burning be transported down to the from high elevation to the near ground base? Later, I induced the major transport base from Indochina. Actually, it's 2,000 and 4,000 meters high. Okay, let's talk about the first question. Actually, I already published last year's we are lucky we have emerged management, aircraft management from the Bremen University, Germany. So we cooperated to take the major. The aircraft is we call it Hello. It's just located in Taiwan, Tainan station, and take the sample to the East China Sea and back to Taiwan. It's around 1 month campaign. So this is the days for the campaigns. So you can see it's from Taiwan, Tainan to take sample, East China Sea and even south of Japan. So the this aircraft is actually take the samples around the aerosol like the OA, black carbon, sulfur, nitrate, ammonia, and the trace gas from the aircraft management, and also the acetone, acetone nitrates, mono OH. Also, so here I introduce two cases. The one is actually no biomass burning transport to this region, which is March 17. And the one another day is heavy transports, March 19. So you can see is the flows, ground base flows actually after from passage. So you can clearly see no easy flow at the near ground base, and the 19 also. But however, you check the high elevation, which means the 700 Pascal, you see is the geographic high. You can see the trough here, and the strong wind just from the southern China to South Korea. This is 17 situation. And however, the 19, you see the trough tilting, and then strong wind just pass over from Indochina to Taiwan. Okay, so this day is a significant transport from the biomass burning biomass product from Indochina to this region. Okay, this is the situation for the from March 18 to 19 for the fire hotspot for Maldives, and AOD we can see is a quite high AOD of this region. So I use not only the measurement, but also use a numeric model, try to simulate this kind of transport and the air pollution issue. Like the I using the Wolfgang version 4.11 and emission, good in Taiwan's emission and China, East Asia, and just modify and the biomass emission using the fin data from ENCA. So the the chemistry module just use the NOAA reckon module, and also module use the MEDA VDS, also use KPP laboratory. So later I will use and analyze the area like the Taiwan here, and the East China Sea, and the South China Sea, and the China. Okay, this is a situation I just mentioned. Biomass burning transport to East China Seas. So from the ground base here, you can clearly see the flow is easterly from this low latitudes and the southerly. Actually, this kind of high aerosol. This is the CO concentration. Actually coming from the biomass burning from Indochina and following the flow just trapped over the South China Sea. And then 3,000 meter high, you see is the transport. The wind flow actually southwesterly here, southerly to southwesterly, but the over this region actually empty. Like this is a difference between biomass burning turn on and turn off. So which means this is a contribution from biomass burning. And then you see we do the trajectory from this region. So you can clearly see from 3,000 meter high actually transport from China. Okay, next day is next episode is in March 19. I just mentioned this is clearly biomass burning transport from Indochina to East China Seas. So you can clearly see 3,000 meter high and even the ground base of high CO concentration. Okay, this is the animation for the difference of for the biomass burning case March 19, and if we take the cross section here, pass over 30 latitude, so you can clearly see the high concentration of CO actually between 2,000 meter high to 4,000 meter high. I call this is a biomass burning plume transport layer. This is a quite clear transport. This is the aircraft measurements from Thailand and to the East China Sea and back to Taiwan. Okay, this is March 17, which means it's actually 5 weeks to transport to the East China Sea. So the altitude, the dash line is the path of the flight, and this is the CO concentration around the 200 to 300 ppb. And if you check the aerosol, once the aircraft is down to the ground base, so you can clearly see the isopropyl pollutant like the sulfate and organic aerosol peaks here, because actually in a low boundary. Then let us check the significant biomass burning transport. So I just mark here when the fly transport to this region. So you can clearly see when the fly to 3,000 meter high and down to the ground surface, and then up to over the 6,000 meter high. You can clearly see two peaks actually consistent for the organic aerosol, and also is the black carbon, which means this is also all the biomass burning product. And also you can see the acetone and acetone nitride. Actually, this is a tracer for the fingerprint for the biomass burning product. It's a peak quite consistent with the fly transfer to the biomass burning transport bed. Okay, so this is quite strong the evidence for the biomass burning transport to this region. And also, if you check the CCN, the OA and the CCN, this is measurement result also can check the quite high concentration of CCN when the aircraft pass over the biomass burning transport band. Because aerosol is a cloud nuclide, so you can see it's quite high CCN over this time transport to the okay. The green line here is in the vertical from the concentration every 500 meter. We have the average and the mean concentration is red solid, and March 17 is blue. So you can clearly see all the species like the OA, aerosol, and the acetone high concentration here, especially for the 2,000 to 4,000 meter high, always as a peak compared to the biomass burning transport. And also, because the high aerosol concentration, so this is in the contrast for the J value, the March 17 is higher J value. Okay. So how good our model simulation? So you can check the observation and the model simulation along the aircraft. So the aerosol, the AgWG, if we compare with these 2 days, the AgWG and the correlation are actually more than 0.5, especially like the NOx, NOY, and NOx is 0.7. And if we just focus on the 2,000 and 4,000 meter high, actually the correlation increasing, which means the biomass burning transport simulation actually like the OA, CO, the correlation with the proportion 0.8, 0.7 for the indicator of the biomass burning transport. So we evaluate the effect of long chains of biomass burning from into China if the elevation lower than 1,000 meter high. Then the contribution of the biomass burning actually less than 20%. This is the biomass burning difference there. So for the all species like an NOx aerosol species. However, if we check the elevation between 2,000 and 4,000 meter high, the contribution from biomass burning could be ranging from 30 to 80%. So this is quite clear for the evidence for the transport of the biomass burning to China. And if we check the cloud water, you see this is a little bit complicated because the solid line is biomass burning cast, and dash line is biomass burning cast for this region, and the different region actually different color. I just would like to highlight here East China Sea is red line. You can clearly see it's the solid line, which means the biomass burning cast with the high contribution from the biomass burning and affect the cloud water difference from this due to the biomass burning increasing the cloud water for this region. So you can image in case the cloud water increasing, so you will reduce the radiation to the ground beds. Okay, so if another case is South China Seas, the blue line. If you remember the pictures actually South China Sea, South China SCA, the area, actually, both of these cases are all affected by the biomass burning. So you can see the solid line and dash line also has high contribution from biomass burning influence. And also, you can calculate the area for the East China Sea is the effect. The solid line is contribution from the biomass difference from the for the control run and the non-biomass emission. So you can see the for the solid line here, and the red line actually the real simulation result. So the air radiation decrease will be around the 2 to 5%. And the indirect effect actually, if the biomass burning actually can affect reduction about 5 to 10%. Actually, this is the compromise for the aerosol and the cloud formation, so it can affect the radiation and to the ground space. Okay, I think this is the first topics. I just highlight here's for the scientific question one, because the biomass burn transport is actually 2,000 to 4,000 meter high, so it also can affect the radiation forcing. This is the link from the climate change, because if this spring season, the biomass burning effect actually can affect the local climate. Okay. The next question, actually, I would like to see introduce about the transport, and if we can, you can image if the biomass burning. Actually, I just introduced the elevation is 2,000, 4,000 meter high. In case can down to the ground base, then it have a significant influence the air quality. Okay. So this is the motivation for another professor in NCU. He proposed a concept, and this concept actually just telling us the western flow and downthrow the due to the northeast monsoon can downthrow, but it just a concept modules. However, the researchers like this one, he performed the chemical data analysis and found actually no evidence that the amount of the smokes can be bring the biomass burning down to the ground surface at the South China Sea. The another researcher also provide observation data from Dongsha Atoll. They find no evidence that the biomass burning can be bring and down to the ground surface. Why? So this is just a concept. So that's my question. Also interesting to understand what kind of situation then the biomass burning can down to the ground surface and affect the air quality. So I use a model also Wolfgang, but I put a tracer just over the fire hotspot, try to evidence how the mechanism of the transport from the high elevation to the to the ground surface. So our simulation, a whole month from February 1 to 30, actually 3 months from February 1 to April 30, 3 months simulation. And this actually, I just mentioned, this is tracer, no chemical. All the evidence just showing from the observation. This the upper one is MODIS and the Himawari 8 and the AONET from the ground surface for the AOD. So this is the March 10, March 16, March 23, and March 25. Clearly sees that sometimes the AOD is weak like the March 10, and the other 2 days, other few days, like the 16 and 25, quite high AOD. If you compare with the Fugui Cap and the Luli Mountain, Fugui Cap is not tip of Taiwan, and the Luli Mountain is over the 3,000 meter high, I just mentioned. So the starting line here is our simulation, and the observation is satellite. So you can clearly see the high AOD occurs just like the sub-17, and our simulation or tracer simulation also showing the high tracer concentration. And the March 10, actually, no tracer. If you check here, because the satellite, but you can see low AOD even for the southern China. Okay, so from the time series, you see sometimes the low concentration tracer like the March 10 and 23. Okay, and sometimes you can see high AOD. So it's depend on the weather condition. Okay, another measurement is LiDAR. You see, this is cap. Where is the cap? The cap is Fugui Cap. It's a North Tip Taiwan and the Luli Mountain. And NTU is Taipei and Dongsha Atoll here. Okay, so 3 LiDAR you can compare with the high AOD transport pattern compared with the time series. So you can see it's quite consistent for the, for example, here and here. What you can see is above the 2,000 meter high has the high base scattering. And here also from 25, see, even the Dongsha Atoll also can show high AOD. So you compare with the time series, this is also the high AOD. Okay, so we back to check the days of the simulation. This is the tracer simulation. I call this type is mountain downslope circulation. So you can see the weather condition, the continental high already moved to the ocean, and Taiwan is here. Okay, you can see the quite stable and weak wind speed. So the simulation tracer, this is all tracer simulation. So you can clearly see this region, and this is a quite high tracer concentration over this region. From the ground surface, actually no tracer. If we check the other day, the March 12th, different timing, you can see over the mountain as a high tracer. So, but however, this is a 3,100 Pascal, which means this is a 3,000 meter high. So the cross section to cross section A here from west to east. So you can clearly see mountain, high mountain here. Tracer is just over the high elevation. And this is, I just mentioned, this kind of wave type is quite stable. So you can see it's the mountain upslope wind and downslope wind during the night time. This is middle night, 18Z, since night time. This is UTC timing, but you see that this local time is 2 a.m. So downslope wind can transport from the high elevation because the mountain in Taiwan actually the peaks around 4,000 meters, and in northern Taiwan also 2,000 to 3,000 meter high. So you can see during the daytime the upslope wind that the tracer concentration over the mountain slope is as concentration low. So actually, under this kind of weather condition, so we can say it's the high mountain, the downslope wind actually can bring the tracer from high elevation to the down to the near ground surface. Another case is I call it as front secondary circulation. So front just patch, and you can see the weather types here. Front here, Taiwan is just past Taiwan, and you can clearly see northerly flow and southerly flow, which means the location front. And you see the near ground surface tracer concentration already passed from north to the south. And high elevation, you see the high tracer concentration cover all Eastern China area. And the causation B, which means this is the causation north to the south. So you can see the flows over the front area. So quite strong upward lifting due to the front. And then to the second, we call it is secondary circulation to the back and the front. So then turn over to the ground surface and then transport the tracer to the south. So I think that this is another type for the front lifting and the secondary circulation bring down to the tracer high elevation to the ground surface. So this is another situation. The third situation I call it mixing. We check the very case and see you see the types, the front formation actually over the southern China. And you all might know is from the ground surface, the tracer is quite strong southerly flow. From the ground surface actually can transport to the southern China. And the southern China actually high mountain. So before the front passage here, over this region, before the front passage, actually, the effect already exists, like the mountain downslope. I just mentioned downslope flow. So you can see here, the before the front passage, high tracer already over the mountain area. And high elevation showing you all cover the high tracers over this region. And the causation, we get the causation C from northwest to the southeast. So it's a little bit complicated, but I just would like to mention actually the mountain effect and the front dynamic secondary circulation to this couple situation. So the concentration is even higher. It's a little bit complicated because the causation is from China to southeast Taiwan. This is Taiwan's mountain. Actually, this kind of case are missing these two types. Okay, we just mentioned actually sometimes the researchers say, hey, no biomass burning transfer to Taiwan region. Actually, it exists. The situation here, this is no biomass burning emission over Taiwan. This is quite high, continental high pressure. So you can see from the source surface, northeasterly, quite strong wind. And even 700 Pascal, you see, no any tracer over Taiwan. And this is March 23. So the evidence is here. The LiDAR also showing 23 is about here. Actually, no high scatter. But however, you can see the Dongsa atoll. See, you can see 23 high the best scatter. Why? It is because atoll is here. Just the bump, just pass over the atoll. Okay, so this kind of situation actually can tell us if the continental high pressure system strong enough, it may not affect Taiwan. because they can push to the south. And the evidence here, tracer simulation, not from the Fugui, Taiwan, also Taiwan, but and also the satellite, also low level. You can see this is I just tell you the situation. So I summarize this kind of mechanism of the long-range transport biomass burning can downward transport. Type 1, mountain downslope circulation. During the nighttime, downslope wind can bring the high tracer or biomass burning product from high elevation to the near ground surface. During daytime, actually just limit the high tracer. And the second one is from the secondary circulation. For the warm air, this is from on air, the uplifting and the secondary circulation down to the back of the front, and then for the strong northerly wind transport to Taiwan. And the third, I just mentioned, is a little bit, it is missing these two types, a little bit complicated, but the mountain downslope circulation already occurs over China. Then from passage, that this kind of complicated transport. And we also calculate the current for the different area. For example, this is, I just would like to mention over Taiwan here, this region, for the three types, the contribution, near surface, and the boundary layer, and above boundary layer. For the Taiwan here, near surface, the mixing type 3, the current, the percentage about the 3.3%, and the boundary layer, which means below 1,500 meters, or 8%, and the second one is from the type of from, rather the mountain effect actually is weaker. Okay, that's I think we use the tracer simulation to identify the mechanism, which means the biomass burning can be done or transport from such an effect the air quality. Okay, so I summary just use the figures because aerosol is a cloud nuclei. So when it to the affect cloud, like our simulation, called water, called and also reduce the radiation forcing to the ground surface. So that's the point for the radiation forcing reducing and affect local or regional climate. Okay, I think I also provide some reference my previous study. So this is my talk. Thank you.
Thank you very much. From the floor to but I have one. So you are saying that the smoke on the top, like up to the come down to the floor, but very small amount, not like the very small.
The to the ground surface actually.
The station is on the ground surface.
Yeah, but it also difficult because we only have the quite few stations over the mountain. So the boundary there below 1,500 meters actually also contribute about can account for nearly 20%, but we don't have the measurements. Only rely on the LiDAR, the profile.
It can, but not high amount.
Yeah,
not that high amount because most of the station on the ground.
But even only the few percentage can downwards, but compared to the ground surface, I think it the contribution in case because if the For example, 100 microgram per meter, only 3% or 5%. So already can contribute 5 to 10 microgram per meter compared to the big one station. It's high.
Unlike like smoke like from Sumatra, it's different kind of smoke that come.
Yeah.
You can see it coming because the characteristic of the smoke in the upper Southeast Asia is not like lower Southeast.
Yeah.
The concentration of the smoke is not thick, but the heat fire creates like thick smoke.
Yeah.
So when it disperses up, getting about something like that. You get big. So it can.
Okay, great talk. I have a question about here because this is my first time to Bangkok. Everything is so great. Okay, transportation is great, and the hotel is great, and
food is great.
Right, but the problem is the air is.
I think you mean the visibility, right?
Right.
So we look out.
What's your opinion on this one?
Yeah, I think that this is also this season also the biomass burning season. But I just talked with the Bertrand this morning. That I think that the significant contribution may be traffic because right now the fire hotspots the much significant fire hotspot, but also already have I think the north of China in January or February already fire hotspot. Now depend on the weather condition can transfer or affect whole region.
So that means one typhoon can solve all the problems.
Oh yeah. And to, yeah.
Thank you. Any further? Yes, please.
Thank you for the presentation. And well, very basic question. But I understand your study. How? For example, global warming.
Due to biomass burning contribute. Yeah, I think.
I basically understand it is something to do with global warming, but I don't know how and how much.
Oh, okay.
Do you have any comment?
Yeah, I think the biomass burning on different season at different area biomass. As in my introduction, actually, I remember it contribute 10 to 15% for the due to biomass burning for the CO or CO2 situation. So I think that this is not due to biomass because different season, different area that's biomass burning. I forgot to provide the global biomass burning. Actually, they do contribute that. Yeah, I remember it's 15% wrong, 15 to 20%. So it can affect the radiation and or the count of emission or the region towards the radiation effect. Yeah, I think that maybe it's around the 10 to 20%, I think.
Any further? Okay, if not, we move on to the second speaker. Professor Wu also have a new title, long one. Professor Wu is that now is from a National Central of University. For Chiang Kai-shek University.
Always like.
Right. Okay. He's now the director of Earth Science Research Promotion Center and director of Interdiscipline program of Earth system, science, Graduate Institute of Hydrological and Oceanic Science. And his topic gonna be about the storm surge and tsunami, something like that. The floor is yours. So we love tsunami. Tsunami happened, we're so happy. Now to go to the
Okay, thanks for Verify's introduction. All right. Now they told me about the all right, because today I look at Verify's face, I realized I should say something about tsunami. Now the storm surge. Okay, so I use the time when Dr. Lee is talking, make another PowerPoint. So, okay. Today I'm going to show you something about the recent development of the tsunami model. One is volcanic tsunami early warning system. The second one is the fast calculation system I made for my students, which can run on my laptop. So this is the first one, the development of compact volcanic tsunami fast calculation system. Okay. So basically, this the motivation is from the Tonga tsunami. So this is the movie of the Tonga tsunami. So the tsunami was not large, but the things was very strange because the whole volcano is still there, but huge tsunami propagated to Japan and to USA. Usually, the volcanic tsunami does not have like this. Volcanic tsunami usually is locally large, but cannot transport for very long distance. This one was not. So I still remember the night my student, our government Central Weather Bureau called me. They say, "Oh, Professor Wu, there was a huge tsunami, huge volcano erupt in the southern hemisphere." And they asked me, "Should we be aware of the tsunami?" And I say, "No, because it's a volcanic tsunami and very far away." But after, I remember after 5 or 6 hours later, then they called me again and they're very nervous. They say, "Well, but you say no, but Japan issued the tsunami early warning, tsunami warning." So I was nervous because usually, there are 2 major tsunami early warning centers in the world. One is Japan, one is USA. USA usually warning something that will not happen. But Japan, once they say yes, then the tsunami will be there. So, okay, so this is the good for Japan's government. So I remember that was after 10 o'clock, so 10 p.m. So I jumped up and asked my student to do the simulation. So this is the simulation result. This is the compact GPU version, which done 1 minute, finish all the simulation. And my student asked me, then how can we do this? I say, well, first of all, so far in the world, there was no tsunami, volcanic tsunami early one. Then they say, how can we do it? I say, easy. Just put a cylinder as a source, like this one. So put the cylinder on the surface. Then my student asked me, how about the radius and the height? I say, well, radius, I say 50 kilometers. And my student asked me why. I say, just I feel so. Then they asked me, how about the height? Okay, I say then 30 meters, and my student asked me still same. So I feel the way. Yes, I say yes. And then this was the result. So then they asked me, then how do we know this assumption is correct? I say, how about there are several like USA dot pool, and they show me the data, and I say, okay, times 1.2, the result. Then this is the final result. It shows that in Japan, the wave height will be around 1.0 to 1.5 meters. In USA, it's about 1.0 meters. And then after the tsunami arrived in Japan, they report, I remember 1.2 something. Very accurate. And then when the tsunami arrived in USA, the number was 1.0. Oh, of course. Yeah, thank you very much. Yeah. Okay. I become their god. They said, how do I know this? So it's very simple. This is the results in 1 minute. Okay. And also we have a CPU version. Previous one was GPU version. This one CPU took 30 minutes to do the whole entire Pacific Ocean simulation. And this is the maximum wave height, and this is arrival time. So 1 week later, USA NOAA give us the result. They use a lot of data data, spend 1 week to get the result. And this was their result. 1 week. This is our result. 1 minute. Thank you very much. That's right. Yeah, I believe it. Okay. All right. So our government was very happy with this result. So they gave us some money, access to build a system for Taiwan for the volcanic tsunami warning. All right, so I use Comcast. So what the secret behind that? Actually, is very simple. This form the superposition principle. The superposition principle says that if the system is linear, then we can do the superposition like just okay. This is a very simple concept. So then the reason is that because it's volcanic and this from very far distance. So from very far distance, so no matter what kind of detailing from Taiwan to look at the Tonga Island, they always look like a point source. The point source will propagate just like a ripple. So the diameter will not be, you can use 50 kilometers, 100 kilometers. The result won't be too much different. We have sensitivity analysis later, but I don't want to show you. I can just tell you the results are very close to each other. And how about the height? The height actually also not important because it says that as long as the system is linear, we can times the factor. So when the tsunami was propagating, passing some dark buoys, I know the fact and I know my simulation, and then I can know the alpha value. Then done. Okay, so very fast and very efficient. But this system cannot handle the volcanic tsunami nearby. It's for long distance. But to be honest, if a volcanic happen nearby, there's no time for it. All right, so this is the system we made, and we use the Tonga Island to test our system, and this is the result, and this is the final result after the superposition coefficient adjustment. And so the result looks like this one I just show you. We have some historical events we put here, and also we have some the simulation domain. If you don't know, the system will tell you how to. If you insist to do something, you can do it. This is the system. So, and the result, this is the result give you the maximum wave height, arrival time, the maximum elevation, and the tidal gauge, the harbor wave height time history. So here I'm going to show you so here I'm going to show you the simulation, the operation, how my student do. So double click, then it should present the result. And we have the location of the volcano and the default value for the tsunami source of the cylinder. Okay, and choose the area. Okay, want. Okay, so you can choose from the near local area, global area, and you can ping the tsunami anywhere on the map, or you can use the historical data, and also you can use Tanka Island event. So you can choose the resolution one. But if you don't know how to do it, we all have a value. So after everything is done, we can click start to run. So the simulation about to begin. So this is on this laptop. This is my first time solar. I don't know how long you can simulate. Okay. And Python is going to plot the result. So here's counting. Okay, so this is the result. It shows the maximum wave time, arrival time, everything. Right. So it's kind of a very simple system that satisfies requirements. And also in the folder you can find those detailed maximum wave time information, and also the arrival time information, also the time history, all the details from there. All right, now we are moving to the next one, which happened in 2024, January 1st. Japan. Noto Peninsula. So in that event, this is the simulation which done by Comcast. It's very fast. And this is our result. And but in that event, the tsunami wasn't very large. The most damage came from space. But this one thing was very interesting. This is the signal we got. This is a tidal gauge signal at the Noto Peninsula. This is time, okay, and this is the surface elevation. So this is called tidal gauge. Usually called to start to use to for the astronomy time. So this yellow curve shows the time history predicted time, and the blue line is the observation time. So usually time prediction is not so difficult. Most of the time, this blue line just follows, just like in the morning. 6 o'clock, you can see the sun. You don't need this one else. But this time it's very strange. Here shows something really happened. So the surface is vibrating. Then big earthquake happened. Tsunami came. So that this tidal station was destroyed. So the elevation jumped to 120, then high. I don't know what happened. That's very high. Anyhow, that's not. So a lot of people saying there was no time for tsunami because the earthquake happened right underneath the ground. The tsunami happened right. So there's no early warning. But I say, wait a second, maybe something can. So there's a gap between. That means the observation is somehow different from the prediction. So if we subtract each other, we got this curve. So that means the water elevation actually being raised for 30 centimeters for 19 hours. If we say the astronomy time, the return period is about 12 hours. But this one is longer than the astronomy time. So there was 3 possible reasons to make this one. One is there was a low pressure passing over. But this one is not because there was winter. And usually it's the winter high pressure system. So we check the data, shows the data is high pressure. The second is because of the Godzilla. So, in Japan, there was Godzilla a lot. So, the temporary don't consider this possibility. The third one, they say, because the ground station was sinking. It's not because the water is rising. Because water rising, the water is fluid. They will separate to anywhere. It's impossible to keep water rising for 19 hours, not falling down. So one possibility is that actually the ground station was sinking and then bouncing back. So why I say that? Actually, that kind of phenomena happened in Taiwan because this is how the earthquake happened between the two tectonic. So one tectonic subduct to the other one. So here is the ocean side, inside is ocean side, and this one up deep is the mountain side. So yes, mountain. So you can see that when the huge earthquake is going to happen, then the tectonic somehow will be locked. Then will make this one give you more and more stress. So more and more stress, that means this ground station has been pushed down for a very long time. The final step is the very small subduction that it was about 30 centimeters. So I expect this the deep down, not deep down, it's subduct. Or we say sleep distance. It's about 4 meters. So 19 hours before there was 0.3 meters. So make this ones subduct, then the whole stress is too strong. Then suddenly release the power, release the energy, and make huge earthquake and the smoke. So if we know we can be aware of this one, actually we have at least 19 hours early warning. So this might be early warning possibility. So here I'm going to show you the recent the model I've been given to try, but we have some updating. So I'm going to show you two different versions, two different cases. One is the case for local tsunami on my LG Gram computer. You know this one, this computer is only for office or sale. So if this, and this one is wrong. This is the event, historical event happened in Taiwan, very small, 7.1 magnitude. All right, just one double click, and the system, all the rest. This one, the script is by MATLAB. We have another version. So MATLAB loaded the script and plot the result. So the small earthquake happened and make a tsunami. We can watch the result, which location changes. You can see that the plotting result take longer time than simulation. Okay, so the first step is done, and this one is second layer, so you can see more clear about how the tsunami attacked the coastal area. And we have third layer. So this one, and we have nuclear power plant here. So like this case give us a hint that if the earthquake was larger, then our area is close under the tsunami threat. Okay, so this is the maximum waypoint and the arrival time, and the time history location for all the locations around Taiwan. So this is this small case. And the next one I'm going to show a case much bigger than this one. Okay, so this is the first case, and I'm going to show the second case. That is a tsunami happened along the Liuqiu trench. So I'm wrong. So this is reading the bathymetry. So the bathymetry file is large. So it covers the Pacific Ocean. But remember this is run on my computer laptop. You have like HPC, and this one run much faster. Usually it's less than 5 minutes. Okay, the simulation is done. first one was the initial surface. The second one is detection of the tsunami propagation. This second layer is local area. And all the harbor time history tsunami height. So this is the model I can probably contribute to this conference. It's just double click, then all right. So this is my first part. All right, and my second part, I'm thinking which one I should. So I think I should show you something like slightly different. That's called analyzing the survival advantage of Clavidiaster libicus. No, not this one. During mass extinction and the impact of hydraulic structure geometry on local scale using this continuous by viscous pattern. All right, this is very interesting topic. I asked my student to do it. All right, the motivation was very straightforward. Taiwan, we have flood. So the bridge under the threat of local scale, like this one, we have a huge bridge, and once the river become is flooding and destroy the bridge. So we want to know how to do the simulation because of local scale. So then we reference to the good old days method. They don't know how to do it, so they use this method, saying, okay, how strong a flood is then the scale. So I don't want to go through the details, and that give you, of course, they'll give you answers, but there are a lot of different parameter settings. Like my study will give you this parameter, because other people study other parameters. So the same equation, they have more than 100 different set of parameters, and all the result they will give you, all the set of the parameter will give you result. The result might be 5 meters, the other one might be 50 meters. So which one you should use? And this one follows civil engineering about. And then so somebody developed like CCHE, they developed a local scale. Okay, so this is a local scale bridge. But they use sediment transport system that requires on this page at least almost 30 parameters. Can you get 30 different parameters in the field? It's impossible. So if you want to write the paper, it's okay. You can just tune all the parameters to then get a very good result. But I don't want to do it. So I make the assumption that based on this one, that is if the shear stress is large enough, then the sediment will be start to move. You can see there's one layer. It's moving. So it's called bed load. So since this just a very simple idea that the shear stress stronger than certain criteria, then so we use the Fallage method. So it's very far from this topic. So then I developed the first one model, which can use this way to do the simulation. And we combined it with another model, which very CPU consuming. It's called Splash 3D. It solves Navier-Stokes equation, it's incompressible continuity and with VOF surface tracking. Okay. So this is all the old things. So we can do the splashing simulation, like a tsunami hitting the structure, or like shaking damage to the nuclear power plant cooling system, and also the tsunami hitting the nuclear power plant reactor, something like this one, or the reactor is okay, but the water intake was destroyed, just like 2011 Tohoku earthquake. So this model has been published, and so I won't go into the details. But I can show you some results, very impressive, that the result can show this curve from here. So this is the simulation, the traditional simulation. This is our simulation. We can see this curve developing, which is so far nobody can solve that. So we do the simulation for historical results by using the traditional method and using our method. So our method shows a very irregular result, and results comparison, of course, this old one, other people's, our new one, very, very close to each other. So since this one has been done, so then jump to this time. I will jump to this page, the one. We say in the history of the Earth, we have been, actually this is not my properly set up. Go back to we have been testing five times extinction. Okay, so number one, number two, number three, number four, number five. The number 5 was dinosaurs. It's called Cretaceous. So why I'm interested in this one, because previously I have been developing a numerical model that can solve the local scale, but we don't know how to protect it. We only know this bridge is going to collapse, but we don't know how to protect it. So I'm thinking, how can we really do something for the bridge? Then there was a hope from the called sea urchin. Sea urchin. This is the very delicious sea urchin which can eat raw. Okay, and we call this one is regular. Regular urchin. Anyhow, just like a sphere. Right? But for the old ancient urchin, one is called irregular urchin. This is the name, Calabius libicus. This the shape is very strange, and so why this one is so important? Because if we look at the time history, this is 66 MA, and the upper part, these two lines are the regular urchin. These two lines are the irregular urchin. And you can see that only the irregular urchin can pass the extinction. The regular urchin died. Why? People say because something say, I have my opinion. My opinion is that, so this is the regular urchin. This is the irregular urchin. And this is the picture for the irregular urchin. So this one is called the reproductive core, this part, and then this mouth. And this is the excretory core. So it's going to use this part to eat the sand, and to release the sand for sandering from this part. And this part is okay. So we think one possibility is that due to the environmental change, such as temperature change, salinity change, pH change, poison concentration change, I cannot tell the difference between this one. They don't make sense. So the irregular urchin can survive in the max extinction, and the regular cannot. The main reason, I think, because of the appearance, shape, they are different. And the irregular have the characteristic of this one, the semi-submergency in the sand, this one. So this they usually submerge themselves in the sand. So as long as it's not exposed to the strong current, it has higher chance to survive. And the irregular shape might have the benefit, might help them to stay stronger. So there are a lot of literature simulation, but they cannot do much about this. In the world, only we have the ability to do the local scholar simulation. Thank you very much. So my student did a lot. My student did a lot of experiments. They built a water tank and paved with the sand. She did very well. So we put the urchin here. One case is facing upstream. The water is coming down from here. The other is facing downstream. So this is the upstream, downstream. And also we consider the regular urchin and also bridge here. So this is the diameter, very small. And I'm going to show you some of the water. So this is the cylinder, and water goes to the cylinder. And this is spherical. You can see the sand. And this one is the urchin facing upward. And this one is urchin facing downward. So this is how she measured the local scour, because the local scour, deeper local scour, make the urchin dangerous. So this is the urchin facing upward, and this urchin facing downward. So you can see that for local scour, this is much bigger than. All right. So of course we use our model, use our system. So this is our validation. We validate this one with a sphere. So the sphere, this is our simulation, and this is the observation, measurement. And I have to tell you, this is probably the world best result so far. Thank you. Yeah, really, this is very difficult. You are in this field, you don't know how difficult it is, because it involves the water, air, and sand. All right, so this is our simulation. Okay, and this is our simulation. One is facing up, one is facing downward. So this is the procession, and this is top view, lots of streamline. So I hope you can see that this very deep scour on the center line, and this is overview. And this is the cylinder. Okay, so the cylinder will also have very large scour going down very deep. That's the major reason that makes the bridge become dangerous. And this is, if you use the square here, then the local scour even stronger, can go so deep, make the foundation unstable. And if you put the urchin, the facing upward, upstream, then also you can see the local scour very strong. But amazing, the magic thing happened. If you put the urchin facing downstream, then almost no local scour. So I was thinking, what if we use urchin, this kind of shape, to protect our bridge? Of course, we will not use this, just combine them together. So this one is the result. Also, again, very small local scour. So this is only the cylinder, only the bridge pile. This is the bridge pile with urchin shape protection. So you can see the local scour was so strong. Here's no local scour. So this is the comparison with cylinder only, cylinder with urchin. So we made the conclusion that Yes, the shape of the irregular ocean actually provide protection to the local skull. And we also noticed that actually we can see this one is called Bachen dune. Bachen dune is caused by strong wind. And the strong wind has over this structure, actually no local skull. It's just like the urchin. Okay. So we make a conclusion that as long as the stagnation point forward than the sand, certain distance, we have a number, then this local scour can be greatly reduced. All right, this is my talk. Thank you very much.
Yes.
Any question?
No, just an information. I'd like to thank you for the tsunami because I was in Vanuatu that night. I remember it.
Thank you.
Plastic that go into the ocean. Just look at it.
It can be any ocean.
Where?
Actually, no South Pole because there was no ocean. Only penguin. Thank you.
Break, and then at 11 o'clock we come back. Thank you. And next speaker, please put the file here. But if you would like to use the laptop, you have to test it first. Might come out.